Billy, there's nobody else at the moment. I'll let them in as you go along.
100%. Okay. Welcome everyone. As I said, a warm welcome. Thank you for joining us in the afternoon and setting a bit of time aside for the concrete class back to basics 1.9. How it will run basically, I'll quickly just run through the Concrete Society, give you the feedback, what we're all about, what we're doing, and the branches and so forth. And then I'll introduce the speaker for the afternoon who's presenting. And we'll have a bit of time at the end for questions that I'll take, and we can take it from there. So without further ado, so the Concrete Society, our 6 core values: modern, advanced, relevant, streamlined and efficient, objective, inclusive and loyal. Our committees: in a branch committee, we have the chairman, Michelle, KwaZulu-Natal branch, Donovan, Western Cape branch, Mari, RMC committee, Prof. Billy. In the fifth committee, head of delegation is Dr. Sarah. And then the cement branch committee, it's Mark. We have membership options. Obviously, there's also half-year fee rates available. If you still want to join, you can definitely contact Natasha, and she can provide you a bit more detail and info. Basically, as you can see here, there's a couple of options that you can join as an individual member or as a company member. And obviously, when you join, you have some benefits as well. Our current members: Diamond members, Krasa and Quick Group. Emerald members, as you can see here, Polstrak, CT's Laboratory, Meteor, Mapai, SNA, all well-known companies. I'm not going to read all of them. We'll just quickly browse through them, not to keep it too long up. Tanzanite members, emerging enterprise members, and associate members. Concrete Fix Season 5, future dates to keep in mind. Concrete Fix 5.12 with Yaku from Afrimat. The Concrete Fix from 5.13 from Bandi Olivier from ACOM. And to Concrete Fix 6.1, also Sarah from the University of Pretoria. Concrete Class Season 1, future dates to keep in mind is on 5 February and 5 March. Branch activities, as you can see here, on the 13th of November, we have a concrete quiz coming up. Workshop durability with presenters Prof. Mark. Purpose of the workshops: introduce the and refresh key aspects of durability index test methods. Branch activities, events to keep in mind: site visits, quarterly technical talks, careers in concrete evenings, networking events, concrete quiz nights and bowls, blitz. And then CPD points. XR CPD points are available to Concrete Society members who are registered engineers with XR and attend Concrete Fix series. And Natasha, you all heard before, will forward an email to all delegates when the CPD points have been finalized and logged on the CSSA's website. A recording and copy of the presentation is also available on the request. And basically, you can just take down how this works here at the bottom, the allocated CPD registration. You basically have this number at the bottom and your attendance reference number. Please visit our website, Concrete Society SA, or you can follow us on LinkedIn. If there's any additional detail, obviously you're always welcome to drop Natasha an email and get any additional information from her. And note here, the success of the society relies on the commitment and support of individuals, companies, and stakeholders from the cement and concrete industry. We thank you for your ongoing contribution. Coming back to today's concrete class, back to basics 1.9. The topic is reinforced concrete design recap, design for flexure with and without axial force. The presenter is Dr. Sarah. She joined the Structures Division of the University of Pretoria in 2011 after 9 years in the design office and is the project leader of the Sanral Integral Bridge Research Team and chairman of the South African delegation. So without further ado, Sarah, I'm going to hand over to you. You can also then start and share your presentation.
Thanks, Philly. Just checking, can you see, is that coming through on your side?
Yes, yeah, I can see your screen.
And it's in presenter mode.
Yes.
Great, cool, thanks. Good afternoon, everyone, and thank you to the Concrete Society for this opportunity just to talk a little bit about the design for flexure with and without axial force for reinforced concrete beams, basically, and columns if you've got axial force. And the intention here is just basically a high-level overview of the structural principles that we're using when we're designing reinforced concrete beams, basically. And you can see I've just put on this title slide here, a beam that we're testing in the lab. This is our Engineering 4.0 lab, our MTS machine, and we're testing, obviously, this in 4-point bending. And you can see the cracking that's happening, which is very typical of a flexural type failure here as we keep loading the structure. So going back to real basics, the first thing we do when we're looking at designing a structure is to analyze the structure, understand what are the effects of the load on the structure. And in any structure, there's only 4 load effects that you can ever get, and they are axial force, it's bending, torsion, and shear. So whatever kind of load you get on the structure, it's going to result in either one of these load effects or a combination of these load effects. And these load effects, axial force, bending, torsion, and shear, if you go back to your strength of materials textbook, you will, in strength of materials, we look at what is the stress distribution resulting from these load effects. And we note when we're looking at what is the actual stress caused by the load on a structure, that we only get 2 different types of stresses. The one type of stress is a normal stress, a stress perpendicular to the cross section. And the other type of stress is a shear stress, which is in the plane of the cross section. And you note that when you're looking at axial force, which is this top left-hand corner here, this is a tensile axial force causing a stress perpendicular to the cross-section. That stress is a uniform stress equal to the intensity of the force divided by the cross-sectional area. When we look at bending, this also causes a stress perpendicular to the cross-section, but the magnitude of the stress varies from a neutral axis point over here, and it varies out towards the outermost fiber. And the equation that I'm sure you'll remember is that stress is equal to my over I. So it's dependent on the magnitude of the load, the distance from this neutral axis, and the stiffness of the cross-section, which is the I value. If we look at the other 2 types of load effects that we get in a structure, shear and torsion, these both cause shear stress. If we're looking at a shear force, it's causing a shear stress that's dependent on the magnitude of the shear force as well as the width of the cross-section. That value T is the width of the cross-section. And that stress distribution is parabolic. So it's 0 at the outermost fiber, and it increases towards the neutral axis. If we look at the stress caused by torsion, it's also a shear stress, and you can see the symbol we use for shear stress is tau. The symbol we use for normal stress is sigma. The torsion shear stress is a linear variation in shear stress, and it varies from 0 at the on the centroid here to a maximum value at the outermost fiber. This is just showing it on a shaft, and we typically use this because, especially with torsion, it's easiest to understand shear stress on a circular section. But we want to look specifically today at bending. So this case over here where we get a normal stress, and we want to combine that with an axial force. In concrete structures, typically we're looking at a compressive axial force, so a force going in the opposite direction. So if we now look at what's happening when a beam bends, the first thing we look at is what kind of deformation or strain do we get in the beam caused by bending. And you'll see over here, if we look at this beam, this rectangular beam, before we apply the moment and after we apply the moment, you'll see that if you draw a whole lot of horizontal and vertical lines, these horizontal lines will become curved with a bending moment, and the vertical lines will remain straight, but they will rotate. And that gives us the starting point to understand what is happening in a beam when we're looking at bending. And if we plot these vertical lines here in terms of the strain profile, we'll see that the strain profile, the deformation profile within the cross section is a straight line. So we have normal strain, which is linear basically, and it's going to change from at a certain point, it's going to change from stretching to basically squashing, going from tension to compression. And that is what we also see with the stress distribution. The strain and the stress distribution are linked, and we would get a linear strain distribution, and when we're in the elastic range, we'll get a linear stress distribution. And in this instance, we would have tension on the bottom and compression on the top, and you would have a tensile stress below this zero strain, zero stress point, which is defined as the neutral axis, and it would vary linearly out towards the outermost fiber. And the relationship here is stress is equal to my over I. That's our classic formula in terms of understanding flexure. So really, this is taking us just to remind ourselves of what's actually happening in terms of flexure. Another helpful thing to use when we're looking at flexure is to look at the principal stresses and the distribution of those principal stresses through a cross section. And here is a simply supported beam with a uniformly distributed load on it. And this is just plotting half of the beam, so there's a center line. Now, just to refresh your memory, principal stresses are the maximum and minimum normal stress, so it's stress perpendicular to the cross section, at any given point, acting on a specific plane where there is no shear stress. So when we look at the principal stresses in the middle of this beam, you will see that they're acting perpendicular to the cross section, specifically the critical outermost fiber points where we get our maximum stress. And as we move towards the sides, the edges of the beam here, so we see that the shear forces causing shear stress are starting to influence the orientation of the principal stresses. And you can see clearly compression stress in the top of the beam and tension stress in the bottom of the beam. And obviously, when we think about concrete, we are really interested in where is their tension, because we know that concrete doesn't handle tension very well, and we obviously need to make a plan, and we do that with our reinforcement. Now, we can also plot stress trajectories, which are basically a set of orthogonal lines that map the direction of the principal stresses, and they help us to visualize the flow of forces through the structure and understand also how to reinforce it. And we can see here the principal stress, tensile stresses here, which are basically parallel to the beam axis over here. And as we move to areas of high shear, we can see that angle changing, and that helps us to understand how the beam is going to behave if we don't reinforce it, and we would reinforce it to withstand these stresses basically. The next thing we need to understand, moving from understanding what are the loads on the structure, what are the stresses that they cause on the structure, we need to now think about how does the material behave under load. So the first graph that I've plotted here, or I've got for you, this is from Roberts and Marshall. It's just looking at compressive stress versus strain for different sample sizes and shapes. And you can see, we know in South Africa, quality control on site cast cubes to verify the compressive stress of the concrete. In America, they use cylinders. You can see if you had the same strength concrete, you would have a higher compressive strength with a cube versus a cylinder. This is because of the reduced confinement that you've got in a cylinder. So a cylinder strength is approximately 80% of the cube strength. So you can see that difference over here. But now we are not looking at something that is just working in compression. We want to look at flexural behavior. So actually, we're looking for the compression strength, the flexural compression strength. And you can see here, if you were plotting the flexural compression strength of a beam with a bending moment, it's approximately 2/3 of the cube strength or 85% of the cylinder strength over here. So that's an important thing to keep in mind. And we also see here that if we're looking at the stress strain behavior of a beam with a moment applied to it, we've got kind of a parabolic stress distribution here up until this strain of approximately 0.002, and then after that we've got a fairly uniform increase in strain with a constant stress level. So this is also a principle that we're going to be using to calculate our moment capacity of a beam. So here is basically this stress strain graph of our concrete on the left hand side here, just plotted next to the simplified stress strain graph for reinforcement. And there's a fairly big difference. You can see we've got a parabolic curve for the concrete, so it's fairly non-linear up until a point where it flatlines basically. The other thing that we're not plotting here is the tensile strength of the concrete. So this is looking at the compression strength of the concrete. The tensile strength of the concrete is fairly low. It's only about 10 to 15% of the compression strength. So concrete doesn't handle tension very well. Yes, it can handle some tension, but we really want the reinforcement to handle the tension, because this is pretty much equally strong in tension as well as compression. We've got a fairly linear stress-strain relationship, and we know that the E value, the stiffness here of the material, is approximately 200 gigapascals until we reach the yield strain, which for our 450 MPa rebar is 0.001957. And after that point, we've got a lot of ductility within the material. So you can see it can handle a lot of strain before you would eventually get to any kind of fracture happening in this. So it's fairly linear in the elastic range, and it's very ductile material as opposed to concrete, which would tend to be more brittle. Sorry, has it? There we go. Cool. Here we go. So on that note, this is an important structural principle that we use to our advantage in structural design, is that we make use of ductility to help us. And before we move on and talk a bit more about ductility, we must just remind ourselves of what ductility is. If I've just got two graphs here, on the left-hand side, we've got the stress-strain graph of a brittle material. On the right-hand side, we've got the stress-strain graph of a ductile material. Now you can see the brittle material over here basically is very little plastic deformation that can happen, and there's very a small amount of strain that happens before you get fracture, and this point would be the point where it fractures. So very little warning before you get failure, as opposed to a ductile material, and this is just looking at structural steel actually, and you can see the stress strain behavior, a lot of deformation happening before you get final fracture over there. So the ductility is basically a measure of the strain deformation that a material can undergo before you get final fracture. The thing what one needs to watch out for in structural steel is as you tweak the strength of the steel, and typically that's done by adding carbon, you can see that yes, you're increasing the amount of stress that it can handle, but you're decreasing the ductility, the amount of strain that happens before you get fracture basically. So that is our just definition of ductility, and it's important to keep that in mind when we are looking at the design for flexure. So now if we take all of this background information and look at what we're trying to do with the reinforced concrete beam, we basically are designing a composite beam where we're using the tension reinforcement to, which is our reinforcement to handle the tension that develops in a beam that's bending, and the concrete on the other side of the neutral axis is going to handle the compression. So this composite action is basically, we need to make sure to enable the composite action, we need to make sure that we've got sufficient bond. So if you had a bond failure, that you couldn't get this kind of composite action. And you can see here that when we are looking at an ultimate limit state design, we would basically be ignoring any contribution of the concrete and tension below the neutral axis, and we assume that the reinforcement is doing all the work, and then above the neutral axis we've got the concrete handling the compression side of things. And basically you end up with this equilibrium situation here where you've got a resultant compression force in the concrete equilibrated by the resultant tension force in the steel, and the moment capacity is, it's a couple moments force times by distance, or force times by lever arm. So that's the principle that we're looking at, and it's a composite design. So if we just move on to from that point, our design assumptions that we're going to be using to come up with our design equations are, first of all, that plane sections remain plane after bending, which is called the Euler-Bernoulli principle. And that's basically saying that we are assuming there is a linear strain distribution in the section, and that any deformation caused by shear is going to be negligible, because shear causes distortion and warping of the cross section. And we're going to say for our principles here in terms of looking at flexure, plane sections remain plane. So again, just back to this principle over here, we've got a straight line strain variation. That's basically what we're saying with plane sections remain plane. The other important assumption is that the stress strain curve for the reinforcing steel is known, that the tensile strength of the concrete is negligible, and we're going to ignore that, and that the stress strain curve for the concrete is known, so we have the magnitude and the distribution of the compressive stress that can develop in the concrete. So those are our assumptions that we use going forward. If we just look at that in a bit more detail, what is happening to the curvature and bending within the beam as we increase the load. This is a nice sketch from, again, Robertson Marshall, just looking at the distribution of stress and strain for flexure as the moment is increased. And this little graph here shows curvature. Curvature is basically defined as the measure of how much the beam would bend. It's the rate of change of the slope of the beam under load. It's the magnitude of the moment divided by the E value and the I value of the material and the cross section, basically. So that's curvature, but it's basically linked to bending and to the amount of deflection that happens. And on the vertical axis, we've got the moment here. And you can see 4 points that I've plotted here. The first point is where the concrete cracks, and you can see very linear behavior until the concrete cracks. And then you get a sudden softening that's happening, so a sudden loss of stiffness as well when the concrete cracks. And now below the neutral axis, we would be ignoring any contribution of the concrete and tension, and now all of that force, that tension force, is going to be assumed to be taken by the reinforcement. Still a fairly linear variation in stress in the concrete until, and if you, in terms of this, if you're looking at, this is still in the linear elastic range, but as the load is increased beyond that point, so this stress distribution in the concrete becomes more and more non-linear and parabolic in distribution, and you get plastic behavior, basically. So this is just helping us to understand what is happening, and you can also see that we've got if this is now what is happening in the structure, a fair amount of ductility in this structure, but we're going to look at that in more detail because this is going to depend on how much reinforcement you've got as to how much ductility you've got in the section. So on that note, what we want to have in our reinforced concrete structures is typically called an under-reinforced beam, where we have a ductile tension failure. And that is basically saying we've got a low enough steel content in the section that the steel yields before the concrete reaches its maximum strain. And we said that maximum strain where concrete would fail brittly in compression is 0.0035. So this is the strain distribution that we want, and this can only be like this if we don't put in too much steel, basically. So we make sure that the steel percentage enables the steel to yield before the concrete crushes, basically. And this would be a tension failure. So we call this an under-reinforced concrete beam, but basically we're forcing the steel to yield before the concrete crushes, which would be a brittle type failure. An over-reinforced concrete beam would be where the steel does not yield and the concrete reaches its maximum capacity before the steel can yield. And you can see here that neutral axis is dropping right down over here, and this would be classified as a compression failure. And this failure would be a brittle type of failure, a very sudden failure. So this is a failure we don't really want in our structures. We'd rather have a lot of warning before we see the failure happening. But here, if the structure, if the element is over reinforced, you would get the concrete maximum strain reached, and that maximum strain is 0.0035 before the steel reaches the strain at which it yields. Now, what our calculations or our formulae are based on is something called a balanced failure, which is where the concrete crushes as the steel yields. So this a percentage of steel would, whatever this, we could calculate what this is, but this would give us a balanced failure, which is concrete crushing as the steel yields. Just to illustrate this further, this is a sketch just show, or a graph, two graphs just showing the, again, moment versus curvature. Curvature on the horizontal axis for an under-reinforced versus an over-reinforced beam. And you can see here the crack moment, M sub CR, is basically that would be very similar for both of them, but we get a lot more ductility out of an under-reinforced beam versus an over-reinforced beam. You can see very sudden failure kind of in the just after the linear elastic region here, you're getting a compression failure versus a lot of plasticity and ductility shown in the under-reinforced beam. And this is something we do every year with our third year class. We show them, we test basically 3 different beams to failure. We first of all test an under-reinforced beam to failure, and then an over-reinforced beam to failure, and then we also look at a shear failure, which I'm not going to talk about shear today, but this is just showing a ductile failure mode. You can see, again, this fairly uniform distribution of cracking happening, which is typical of something that's busy working in bending. There's flexure happening here. You can see these crack widths. Again, if you only had one crack, then there's probably very little bending happening here. That would be synonymous of some kind of restraint, so some kind of restrained shrinkage, etc. But when there's flexure, you would see these fairly uniformly distributed cracks, so that you can follow the curvature of the beam here. And there's another just view of this, just showing the bend. You can actually see the deflection here, and you can see these uniformly distributed cracks. And eventually you would go past, obviously the steel would start to yield, and a final failure would be when the concrete crushes eventually over here. But if you had an over-reinforced beam which had a brittle failure mode, now you can see much smaller cracks, and then all of a sudden this brittle failure where the concrete suddenly crushes, and that's your over-reinforced beam. So again, we're using the term under-reinforced versus over-reinforced. Obviously, you're designing it for your load effects, but if you put in too much reinforcement, if it eventually gets to failure, you would prefer to have a ductile failure mode as opposed to a sudden brittle failure mode. Here's another view of this, and again you can see much smaller cracks, fewer cracks, and then at the sudden mode of failure here. Sorry if you're hearing strange sounds from my mic. We've got a storm happening here at Pretoria, so there's a bit of thunder behind me. Okay, so just back to recapping on this, you can just sort of see the progression of strain and stress distribution as we're moving from a moment pre-cracking. We've got, again, a linear strain distribution and a linear stress distribution. We would calculate our resultant forces in tension and compression, and we'd be able to calculate what that moment is, or that would be equal to the moment applied. After cracking, we ignore any contribution of the concrete and tension. And again, we're still looking at equilibrium. So the tension and compression forces need to equilibrate, and the moment is equal to the force times by the lever arm. Now we are, again, still, if we before the ultimate moment, we are lower than this maximum concrete strain that concrete can handle. And if we now look at the ultimate moment the section can handle, now we are taking the strain in the concrete to its maximum, 0.0035, and we would be looking at a parabolic stress distribution, which we'll talk about now, and again equilibrating horizontal tension and compression forces and calculating what that resultant compression forces in the compression side and equilibrating that with the steel. If we now say, well, let's look at designing this for our limit state design method, we use partial material factors and we also use load factors to come up with an acceptable probability of failure. And when we're looking at reinforced concrete design for flexure and axial force, our partial material factor is 1.5, and our partial material factor on the reinforcing is 1.15. There are other factors in terms of shear and bond, 1.4. This, I think, in the new code we are adopting has become 1.5, but that's something I need to verify. But you can see what the other factors are. And then when we're looking at serviceability in terms of loading, we're coming down to 1. So now using our partial material factor of 1.5 and knowing that in terms of bending of a beam, we can only use 85% of our cylinder strength, and I'm working with cylinder strength here because that's what the Eurocode does, and we are going that route. So these sketches are for cylinder strength, not cube strength. When we are looking at the ultimate limit states, we have our parabolic stress distribution, which for ease of calculation, we use an equivalent rectangular stress block, which has got exactly the same resultant force. So this resultant force from the parabolic stress block, if you use 80%, 0.8 of the depth of the neutral axis, we can calculate the same resultant force, F sub cc, and the position of the resultant force would be the same. It would be at half of the depth of the stress block of that 0.8x. So that's going to give us the same effect as the parabolic stress block. It just makes the calculations easier. This is something that has changed from the old code to the new code. In SANS 10100 part 1, this was 0.9, so it's now 0.8. So just something to be aware of looking as we go forward into using our the adopted Eurocode. And the maximum stress here is going to be that 0.85 times the cylinder strength. We divide that by a partial material factor of 1.5. So that's where the 0.567 F sub CK comes from. And that's basically our equilibrium equation that we are applying. And we set a limit on the depth of the neutral axis. We don't want this to go too low, otherwise we're going to get our brittle failure mode. We're going to have our over-reinforced brittle failure mode. So we set that at 0.45 times D. Just if we look at now this sort of just ending on this concept of flexural ductility, we can basically, if we think about concrete, obviously it's brittle by nature, but we can overcome this by allowing the ductile reinforcement to control the structural behavior. And that's basically what we're doing with an under-reinforced beam. We're letting the ductile material govern, basically. But we can only do that if we don't put too much reinforcement in it. So if we increase the reinforcement content, that now needs a deeper stress block to equilibrate the tension force in the steel, and that that drop in.
You're busy today. I have to come tomorrow.
Sorry, thanks. So that drop in the neutral axis leads to an increase in strain in the concrete, and that results in a loss in ductility. And you can just see that here with this plots of moment versus curvature for low, medium, and high reinforced contents. You can see the more curvature you can handle in the cross section, the more ductile the failure mode is going to be. So that's just showing as you increase the amount of reinforcement, yes, you do increase the moment it can carry, but you decrease the ductility. So then when we're looking at the design of a reinforced section, and this is now what we call a singly reinforced cross section. So we've just got tension reinforcement at the bottom here, to make sure that we've got enough ductility. We limit the depth of the stress block to 0.45 times the effective depth, D. This is typically corresponding with a steel percentage of around about 1.2%. We would start by checking what the limiting moment is without any compression reinforcement. And these are the two equations that you would use if you're using cylinder strength and cube strength. And then if you had a moment that's less than the maximum moment without compression reinforcement, you would calculate a neutral axis depth factor, a K factor, and you would use that to calculate this Z value, your lever arm, the distance between the centroid of the compression force and the centroid of your reinforcement. And you could then calculate, once you've got that lever arm, you can calculate the amount of moment reinforcement that you require for your applied moment, basically. If we now can't get the section to work with just tension reinforcement, yes, we can add compression reinforcement, which now is going to increase the strength of the cross section. It's going to increase the lever arm, and it's also going to help you with ductility, because now in your compression zone, you've got a ductile material, so that's going to help. And it helps with confinement, so it can increase the strain capacity of the cross section. The one important thing to note is that yes, on the tension side, that the tension steel might be yielding, but not necessarily in the compression side. So you would need to calculate what the stress is in the compression steel, depending on the strain that's in the compression steel. But again, in terms of calculating the moment capacity of the doubly reinforced section, we would be applying principles of equilibrium. So the sum of the tension forces must be equilibrated by the sum of the compression forces, and we would be looking at the moment resistance would be equal to, typically we take moments about the reinforcement, so we would be saying it's equal to the moments of the compression force, so about the reinforcement plus the moment of the compression steel about that reinforcement. And that's how we calculate the moment capacity. So that's just looking at flexure, but for a rectangular section, but most real sections and real structures are tied into a slab. So we basically are dealing with a T section. And now we've got, if we're looking at just a simply supported beam, you can see bending moment diagram, sagging moment at the midspan here. And now at the midspan, obviously the compression block is going to be in the flange of the T section. And how much of that flange can you use for that compression block is the question we need to ask, because we can kind of guess that the stress distribution, the longitudinal compression stress distribution in that top flange is probably not and is not going to be uniform. And we obviously are assuming a uniform stress distribution. So we would then need to calculate an equivalent effective flange width, which is sometimes, if these beams are spaced close enough, equal to the spacing of the beams, but most of the time it's not. So we need to calculate what that is for a T section, and that's important. And it's going to be linked to the span, the length of the beam that it's spanning, and the distance between the points of contraflexure. So because you're looking at the sagging moment region, basically. But on that note, this is only applicable for sagging moments. When we're looking at hogging moments, then basically the flange section is considered to be cracked. So then you're only looking at the width of the web, basically, as contributing to the compression, well, carrying compression, basically. So that's just in terms of real behavior. We are needing to look at how much of the flange can we use to carry the compression force, basically, and that we do with an effective width. And if it's on the edge, you would also be looking at the effective width of the L section there, basically. And we would be obviously needing to determine where that neutral axis lies. I mean, where are you going from compression to tension or vice versa? That's the neutral axis position. And if for a T section, it could be in the flange, and then basically we treat it like a rectangular section. But if it falls within the web, if it's a bit deeper or lower in the section, now we need to take into account the fact that we've got two different widths here. Just to actually also note on this is just a section or a sketch that's based on SANS 10100, where we had our equivalent stress block as 0.9 times by X. So just a note on that, it's now 0.8 times by X. And lastly, before we now add axial force to the equation, just a note on stability. When we are looking at structural steel beams, one of the big failure modes that we need to think about is buckling and lateral torsional buckling. Now, typically concrete beams are not susceptible to this mode of failure, but if you had a very slender, thin kind of beam, so where your length to width ratio is greater than 60 if it's simply supported or continuous, or 25 if it's a cantilever, then one would need to be just watch out for beam buckling, and it's something you would need to consider. Most cases it's not an issue, but you need to just be careful of that. So now coming to the end, now we've saw at the beginning, we've got bending as well as axial force, both causing normal stress. And in a lot of elements in a structure, you've got both of these things. So now we need to think about flexure and axial force together, because they're both causing normal stress, and we obviously have to design it to resist both of these things. Now, if we just take this back to very basics, if we had a compression resistance of a cross section, which is C sub R, and a moment resistance, which is equal to M sub R, if we put the full compression force on that element, so C was equal to the applied load was equal to the resistance, that ratio would be equal to 1. And we would not have any extra capacity for any additional moment. Similarly, if we put the full moment on moment resistance, or whatever the maximum moment was, onto the section, the ratio of applied moment to resistance would be 1, and we would not have any room left in terms of the capacity of the section for any axial force. But if you have something in between where you're applying, for example, over here, a compression force which is here about approximately half of the compression resistance capacity, and we came out to some points over here. There's our moment divided by MR, and the intersection of those is lying somewhere over here. We would have a section that could carry a combination of compression force and moment resistance. And the very basic sort of limiting line would be this interaction diagram, basically linking the ratio of compression force and ratio of moment of 1. If we're on this side of the graph, we are safe. If we're on that side of the graph, we're not safe, basically. So that's just basically thinking about now combining these two load effects, which both cause the same kind of stress. But reinforced concrete actually doesn't work exactly like this. This would basically be that line over here, going from pure bending to pure compression. But we actually see that adding axial force can increase the bending capacity. It basically is shifting the neutral axis and helping us to use the concrete's compressive strength, and it kind of counteracts the bending moment. And we see that the interaction between axial force again on the vertical axis and the amount of moment that it can carry comes outwards here to a balance point where we have concrete failing in compression. So we reach our maximum compression stress as the steel reaches the yield stress, and then back to your pure compression, maximum compression force over there. So we've got pure bending on the bottom axis at point A over here, which is basically beam behavior. And we've got pure compression at point C over here, which is basically a pure column behavior. And any kind of tension reinforcement here would be actually working in compression. Everything would be yielding in compression. And you've got this balance point over here where below the balance point, we have a tension failure mode where the reinforcement is going to yield before the concrete crushes. And above the balance point, if we're somewhere there, we've got a compression failure mode where the concrete is going to crush before the reinforcement yields. So this is the interaction between pure bend or between bending and compression, which we see with the design of columns, because most columns have got a certain amount of bending moment that's also attached to them. But I just think it's interesting to note basically almost the pre-stressing effect, if you want to call it that, of the additional capacity that you get in terms of bending as we apply a compression force on the system. If we're just looking at now designing for flexure and axial force, again, we see these principles of equilibrium of forces, the compatibility of strain, and our known stress-strain relationship, and we use that to set up our design equations. So we sum the forces, and again, obviously this would probably be a column, so it'd be vertical, but if we're just representing it horizontally here, the forces on the compression side in terms of the steel and the resultant force in the concrete, you've got the resultant force in the steel and tension over here, and you would be taking moments. Typically here it's taken about the axial force over there in, and you can then also start to set up what we know as MN interaction diagrams, where we can plot now here, typically it's the axial force divided by the cross-sectional area, B times H, and the moment divided by BH squared. For different percentage of reinforcement, we can see what the moment axial force interaction diagram would look like. And these have been developed for various obviously steel percentages, as well as a ratio of where effective depth, sorry, D value over here. So this is specifically for different D values in terms of H, and can also be rewritten to not take, so we take out the compression stress here, C sub U. So here we can use it for different values of cube strength, these would be the MEN diagrams. And obviously now as we move towards using a cylinder strength, this is just from the concrete center. You can also develop these moment axial force interaction diagrams for, again, various D to H ratios. Lastly, just one other thing to watch out for is slender columns, where we get now we could go into the realm of buckling influencing the capacity of the beam. If you look at the failure of a short column, you can see here is the load applied and the eccentricity. That would be the moment N times by E, and there would be your capacity of the material bound failure of a short column. But as you start to reduce the stiffness and it becomes more and more slender, so we start getting second order effects, additional deflection in the structure starting to influence the magnitude of the moment, and you start seeing the axial force that you can carry comes down because you've got more and more moment, until you get into the realm of actually you moving from a material bound failure to a stability or a buckling failure. So it's something to watch out for. And these slender columns can be complex to design, and you need to think about them carefully. So in conclusion, I've just kind of tried to give an overview of what are the important principles that we are actually considering when we're looking at flexural design. The first one is we need to know what the loads are, and then what are the load effects. And there are only 4: moments, shear, torsion, and axial force. That's either tension or compression. And those 4 load effects are causing either normal stress or shear stress. And we are basically looking at designing the structure for moments and axial force for normal stress. Ductility is a really important principle that we are using, and we want in our structures. So that's really important, and that is illustrated in the fact that the under-reinforced versus over-reinforced. It's not to say it's not properly designed, but you just don't want to over-reinforce it that you force a brittle failure. The concept of shear lag is also very important, because most beams are going to have some kind of slab attached to them, and we can't say that the full slab is going to carry the load. There's a decrease in load as and that compression stress as we move outwards from the web of the beam. And lastly, just you can see the principle of equilibrium is essential. Equilibrium of forces, the compatibility of strain, and our stress-strain relationships are essential in terms of setting up these design equations. Just lastly, some references that I find very helpful. Park and Pauly is a classic, and obviously I've relied heavily on Robertson Marshall from the analysis and design of reinforced concrete structures. And our textbook that we're using at the moment for the Eurocode is by Mosley, Bunge, and Hulse, Reinforced Concrete Design to Eurocode 2. And then just a reminder that this is our new concrete code, SANS 51992, part 1, and it's basically our adoption of the Eurocode standard for reinforced concrete design. So thank you. Any questions? Billy, back to you.
Okay. Yes, thank you, Sarah, for this concrete class. I think all of us learned quite a lot, and I think, yeah, if we can open the floor to maybe some questions from the attendees. If you can raise your hand if you have a question, and I'll to you. I see we have a question there from Grant.
Thanks,
Yes,
Sarah.
Grant.
Thank you. Great presentation. Just in terms of the adoption of the new code, has that been promulgated completely?
As far as I'm aware, yes. So it is now officially our code. I don't know if there's anyone else who knows any more about that, but as far as I'm aware, yes, there were issues in terms of getting hold of it. I know that. I don't know if those have been sorted out, but yes, that is our official new code.
Okay. And do you know if part 2 of SANS 10100 has also been replaced, or is that still hasn't been withdrawn?
That I'm not sure of. Good question, and should find that out. I'm not sure.
Okay, thanks.
Grant, can I maybe ask you, you can just pop a mail to Natasha as well. We will also follow up from our side for you.
Yeah, we'll do. Thank you.
And maybe another question around the table. Don't see anyone else. Last chance. Okay, I think that's it. Thank you, Sarah, for the presentation. You've enjoyed it, and I think yeah, definitely. I'll also see from my side if I can find out about that part too. It's actually a good question.
Yeah, we need to clarify that to know.
Yeah. Of course. And then thank you everyone for attending this concrete class. Much appreciated. We'll see you soon, and maybe Sarah and Natasha, if you can stay on.
Sure, Willie.